Hi, I'm Dave Landsman, Senior Director of Industry Standards and Distinguished Engineer at Western Digital. I've also been an NVMe board member since 2011, and today I'll be discussing NVMe ZNS, or so-called zoned namespaces. NVMe ZNS actually evolved from the emergence of zone storage, or so-called zone storage in the HDD world. Nearly 10 years ago now, HDD users wanted to use an emerging HDD technology called shingled magnetic recording, or SMR. Now, SMR drives increase their areal density. In other words, they pack the most bits into the smallest amount of space by enabling tracks on the media to be more closely spaced than they are when they're written on conventional magnetic recording drives. But the price for writing tracks closer to each other on the media is that writing one track partially overlaps the adjacent track. And due to this track overlap, it's essential that one writes to an SMR drive sequentially. This will give you the best throughput and the most predictable I/O latency. The sequential write requirement for SMR spurred the development of command standards to enable zone storage. There are two such standards: the ZAC and ZBC. ZAC is zone aware commands for SATA drives, and ZBC is zone block commands for SCSI drives. And in both cases, the zone storage model defined by ZAC and ZBC divides the device into a series of fixed length regions called zones. And these zones are written according to various rules defined by the zone type. And the most common zone type is sequential write required. Now, when we shift to SSDs, most users want zoned SSDs for the same reason they want zoned HDDs. That is, they want to get the highest capacity possible and the lowest cost per bit. So in an SSD, the technology for getting the highest capacity is QLC NAND, or quad level cell, where you get 4 bits per cell. Now, QLC NAND based SSDs tend to be slower, lower performance, and they also have less endurance than 3-level cell or single level cell SSDs. So they have less performance and they wear out sooner. And just like SMR HDDs, you get the best performance and predictability out of QLC SSDs by writing sequentially to them. Similar to ZAC and ZBC, ZNS divides a drive into a series of fixed length zones governed by write rules. In the ZNS case, the region that we're dividing up is an NVMe namespace. A ZNS device maintains a write pointer in each zone. The write pointer determines where the next data in that zone must be written. It gets incremented on each write operation. And in general, all writes to a ZNS zone must be sequential, and any write to a zone which does not append data at the write pointer is rejected by the device. There is a capability which enables some limited random writes to ZNS zones. It's called zone random write area, but I'm not going to cover that here. When the data in a zone is no longer needed by the host, the write pointer is reset and the zone can then be rewritten starting at the beginning of the zone. In SSDs, this doesn't happen in HDDs, but in SSDs, there can also be events called excursions, where a zone has been opened for writing for what the device deems to be too long of a time, and so we may lose data. And for that reason, the device may close that zone to preserve data reliability. The ZNS command set defines only 3 new commands in NVMe. The zone management send and receive are for open, closing, and resetting, and getting zone status, etc. They're management commands. The third command is zone append. And zone append enables the host to issue multiple writes to a zone, but not have to worry about their execution order within the drive. And they can still be assured that the data is written sequentially on the media, even though the host doesn't have to worry about ordering, and the data does get written sequentially on the drive. All other commands issued to a ZNS drive are standard NVMe command set commands. The advantages of ZNS for SSDs derives from the fact that it enables sequential writes. Fundamentally, using this placement model has several advantages for SSDs. First, as I noted before, most users who want a ZNS device are focused on capacity and cost per bit. This means they want QLC NAND-based SSDs. Writing sequentially to QLC results in better performance, more predictable latency, and greater endurance because it reduces write amplification and the additional garbage collection that causes. Second, and this is also related to the focus on cost per bit, these users want to reduce or eliminate over-provisioning on the device. Over-provisioning is the spare capacity used by an SSD when it must rearrange data amongst flash blocks. We call this garbage collection. So a standard SSD being used for compute applications with random I/O has typically 7 to 28% of its capacity set aside for over-provisioning. This capacity then is not available for user data. So ZNS enables a model close to 0% OP because the drive does not become fragmented, and thus we're delivering more of the media's capacity to the user. Lastly, a ZNS drive can save on DRAM, in other words, device cost, versus a standard SSD. The reason for this is that SSDs maintain an L to P, a logical to physical table in device-based DRAM, and this table is used to map logical blocks to physical blocks. As device capacity goes up, these tables get big, and QLC-based devices are accelerating this trend because QLC gives you more capacity, so the tables get even bigger. On a ZNS device, the L to P table only needs to map the starting LBA of each zone versus mapping each individual LBA on the device. Since there are far fewer zones than LBAs, the LBA L to P table in a ZNS device can be much smaller than one in a standard SSD, and this reduces DRAM needs and thus cost. There are a number of markets that will benefit from ZNS adoption. ZNS offers essential benefits to hyperscale data centers, to enterprise storage systems, and to a variety of use cases in each of these segments. Cloud data center vendors tend to invest in customized software stacks, and some of them are integrating zone storage directly into those stacks. Another option is where customers build applications on top of middleware. WD, Samsung, and others are working to optimize middleware platforms, for example, like RocksDB, Ceph, and Hadoop, to enable apps that run on top of these databases or these systems to gain advantage from ZNS drives. Lastly, the Linux kernel and file systems have been optimized for ZNS SSDs, and this enables standard unchanged applications using the POSIX file system to gain advantage from ZNS. So there's many levels at which applications can be enabled and take advantage of ZNS. Also note that this enabling work has been done for ZAC, ZBC, and SMR HDDs. So we're building a whole zone storage ecosystem around SSDs and HDDs. So, and I like to say always that in our zone storage efforts, we are, to paraphrase Woodrow Wilson's slogan, making the world safe for sequential I/O. There were no functional changes made to ZNS when we integrated it into NVMe 2.0. We simply updated the original TP to fit into the new structure of the refactored NVMe spec family. Western Digital, Samsung, and others are actively optimizing software and tools across the ecosystem to enable ZNS. There are basically three ways in which developers can take advantage of ZNS today. Firstly, they can take advantage of Linux kernel enabling. By using zone-aware file systems like ButterFS and F2FS, applications can just run unchanged on top of a zone storage system and gain some advantages. Secondly, developers can take advantage of middleware, which is optimized for ZNS, such as RocksDB, Ceph, or Hadoop. Lastly, developers can enhance applications directly using user mode libraries such as libzbd, libzbc, or XNVMe. And a great resource to learn about all of this ZNS enabling is zonestorage.io. You can visit the NVM Express website, and please head to the NVM Express YouTube channels where you'll learn a lot more about NVMe 2.0 specifications, new command set specifications, and all things NVMe.